Hello, everyone. Welcome to Friday Happy Math Hour. Today, we're going to talk a little bit about functions, evaluating functions and the domain, and one of our favorite topics, difference quotient. At any time, if you have any questions, please let us know. You can raise your hand, put it in the chat. And then also, if you want a copy of this presentation, you should see a little box with an arrow where my pointer is at. You can click that and it'll allow you to download the presentation. So we want to know what is a function. So here are some definitions that we're going to be looking at. The row of a correspondence that relates two quantities is called a relation, and a relation is a set of ordered pairs. An ordered pair is, for example, 1, 2 here would be an ordered pair. The set of all first components of each ordered pair is called the domain. So in this example, if we look at all the first components, which would be 1, 3, and 5, that is what makes up our domain. The set of all second components is called the range. So the second component of that ordered pair would be a 2, a 4, and a 6. And so that would make up our range. Another word that we use for domain that you might hear some of your instructors say is the word input. So all the inputs are what make up the domain, and all the outputs is what makes up the range. Now, in math, we have a lot of relations, but there is one special relation, and that is called a function, which is what we will be looking at throughout all of your math courses. So a function is just a special relation, and basically what it is if we look at two sets, set A and set B, set A being the domain and set B is the range, it's a relation that assigns to each element X in the set A exactly one element in set B. So in other words, if you look at all your first components, so in this case 1, 3, and 5, the question you want to ask yourself is does 1 go to exactly one element in the range? So in this case 1 goes to 2, and if you notice over here there's no more 1 going anywhere else. And then 3 goes to 4 and 5 goes to 6. So that would make this a function. So here we have some different examples that is going to make it a little bit more clear. So these are all relations right now, but we want to know if these relations are functions. And so they give us a picture, so we'll look at each of them separately. And each of the pictures has a domain and a range. And then they have the elements of the domain and the range. And so if we look at the first one, what you want to ask yourself is, does each element in set A, which is the domain, correspond to only one element in set B, which is the range? So let's take a closer look. So here you can say that 1 goes to exactly 0, 2 goes to exactly -8, and 3 goes to exactly 6. And so in other words, 1 goes to one thing over here, 2 goes to one thing in the range, and 3 goes to one thing in the range. So that's going to make it a function. Let's look at letter B. In letter B, 8 goes exactly to the number 5, 7 goes to number 9, 2 goes to number 3, -3, and -4 goes to 5. Notice here that 5 is repeated twice, but it doesn't matter as long as the domain goes to exactly one number. So in this example, this is still a function. Now let's look at 3. 3 looks a little bit different because they're all going to one number, but the question is, does 7 go to exactly one element in the range? And the answer to that is yes, 7 is going to only 30, and -5 goes to just 30, 6 goes to 30, and 8 goes to 30. So they're all going to the same thing, but that doesn't matter because they're all going to exactly one thing. So that's still going to be a function. the difference now here with letter D, if you notice 8. So the question is, does 8 go to just one element in the range? So here 8 goes to -5, 8 goes to 8, and 8 goes to 7. So 8 is going to 3 different elements over here, and that's going to cause it to not be a function. Okay. So if we were always given these pictures, then it would make things a lot easier, but we're not always given those pictures, right? So here's another way that you might see this. They might ask you to determine whether each relation is a function. So we're going to look at letter A, B, and C. Well, one thing that we can do is, if you really like the pictures, then what we can do is we can draw our own picture. So here for set A, I have my domain is made up of all the first components. So that's 1, 3, and 5. So I can write them down here. And then my range is all the second components, which is 2, 4, and 6. In the order pair, 1 goes to 2, so I draw my arrow. 3 goes to 4, and 5 goes to 6. So all of my domains are going to exactly one thing in my range. Therefore, it's going to make it a function. Let's look at letter B. Okay, so here my domain is 4, 5, 7, and 6. So I write 4, 5, 7, and 6. My range is 0, 10, 8, and 10. So I have 0, 10, and 8. Notice that I didn't write the 10 twice. You could, but it makes it easier if it's just written once. So now we ask the question, does 4 go to just one element in the range? Yes. Does 5 go to one thing? Yes. Does 7 go to one element? Yes. And 6 goes to one element. So this is still going to be a function. Now, sometimes you don't want to be drawing these pictures over and over and over. You can if you want to, but there is a kind of like a little shortcut that you can do these a little bit quicker. So here, the shortcut is, if the domain does not repeat, then it's going to be a function. Okay. So the way we look at that is, for letter C, I'm going to circle my numbers in the domain, and I'm going to ask myself, does the -5, the 1, the 4, or the 2 repeat? And they don't. So that's going to make it a function. Okay. So why don't you guys try this for a second? We have -1, 9, 2, 4, 8, -7, -1, and 30. Okay, so ask yourself, is this going to be a function or not a function? So what do you guys think?
It would be not a function because it's repeated, right? The -1.
Correct.
Okay.
All right. So as I didn't see who said the answer, but as you can see, our -1 is repeated twice. Therefore, this is not going to be a function. Okay. Let's try a different problem. So sometimes, instead of getting a set of ordered pairs, you might have a graph. And so we want to know, is this going to be a function? So we can use what we call a vertical line test. And basically, the way this works is, if you draw a vertical line on your graph, if the line touches the graph in more than one place, then it's not going to be a function. And we'll see in the first picture that if I draw a vertical line here, it's touching in this location and this location. So it makes it not a function. But why does that work? If you notice here, this is your x-axis, which is your domain. So at -3, we would get this as an answer, as an output, but -3 would also give us this as an output. So that -3 would be repeated twice because it's going to be for this answer and this answer. Okay, so if we look at the second graph, if we draw a vertical line test, if we draw a vertical line, and it doesn't matter where you draw it on the graph, if you notice here, if I draw my vertical line test, it only touches in one point. So that's going to be a function. And then the third one, if we draw a vertical line test, it's going to touch in two places. So that's going to be not a function. Okay. So again, we started off with having a picture, and then we had the set of ordered pairs like this one, and then we had the graphs. But what if they ask us, let me keep going here. What if they give us this, right? Determine whether each equation represents y as a function of x. So here we're no longer given a picture a picture or a set of ordered pairs or a graph. Now we just have the equations. Okay, so let me go ahead and take my pen out. So one way to do this would be if we had the graphs, then that would be amazing because we can just draw the vertical line test. Now, at least for me, one of my goals for my classes is that before the end of the semester, you'll be able to look at this equation and you'll be able to have an idea of what the graph looks like. You'll be able to see this, you'll have an idea of what that looks like, and then you'll see this and you'll be like, oh, I recognize that. Okay. So if you know what the graph is going to look like, then it'll make things a little bit easier. So I'm going to just kind of sketch, if we have this equation, then the graph for this is going to be a line. And I'm just going to sketch it right now, but it's going to look something like this. And so with that, pass the vertical line test. What do you guys think? So that would pass the vertical line test, right? Now for the second one, and it's okay if you're not sure right now what the graphs are supposed to look like, don't worry because you'll have some lessons where you're going to learn what these graphs should look like. So for this one, this is a parabola, and I'm just going to draw like a sketch, but the shape of this graph is going to be something like this. So that would also pass the vertical line test, and so that would be a function as well. For letter C, your graph actually it's going to look something like this. And so that would fail the vertical line test. And then the last one is a circle. So anytime that you have x squared and y squared, it's going to be a circle. And so that would fail the vertical line test. Okay. Now I'm going to go ahead and show you algebraically how we would figure these out. So let's say that you're taking a test, and there might be an easier way to clear the whole screen, but I'm going to go ahead and keep erasing this way. Um, if anybody else knows how to just click and clear, feel free to do that. But anyways, let's say you're taking a test, and thank you, and you have this question on the exam, and it asks you to figure out if it's a function or not, but you don't remember the graphs. Then you can still work these out algebraically. So what you want to ask yourself is, if I choose, remember when we were graphing earlier for X and Y, and you could pick any buttons. I mean, I read the text message. And you could click, you can choose any X values for your equation so that you can know what the graph looks like. So for these, it's something similar. You can try, let's say, some negative numbers, and it doesn't matter what you pick. And then let's try 0 and 1. Okay. So you want to ask yourself, if I plug in this -1 in for my X here, then I get -1 plus 8, which is going to be a 7. So -1 is going to so -1, let me get my pen back. Hold on, I just got out of my whole screen. Okay, there we go. So -1, we just said, would give me a +7. Well, what about 0? If we plug in 0 for X here, it's going to give me an 8. And I always want to try a positive number as well. If I plug in 1 for x, I get 9. So each of these is resulting in just one element in my y in my range. So for every x that I choose, it doesn't matter what I choose, it's always going to give me one y. So this is going to be a function. Okay, so let's look at letter B. So I personally always like to solve for y. So this would be 4x squared plus 36. And then we can try the same. This is x, this is y. I'm going to pick a negative number. And it could be negative 100 if you wanted it to be, as long as you try a negative number in there. So negative 1 for x would be negative 1 squared, which is a positive 1, plus 4 is, times 4 is 4, plus 36, that's going to give us a 40. But notice that no matter how hard you try, if you plug in negative 1, you're always going to get 40. It's not going to give you two answers. Okay. Same for 0. If I plug in 0 for x, then I only get 36. And then last, if I plug in a 1, I'm going to get 40. So you might be thinking, oh, that gave us a 40 here and a 40 here. So you might be thinking, oh, that gave us a 40 here and a 40 here. But remember, the y value, it doesn't matter if that's repeated, as long as your x values are not repeated. And the number 1 is always going to provide a 40. It's never going to give you anything else. And so this is also a function. Okay. But let's see what happens with this guy here. So remember earlier I said always solve for y. Okay, so that's what I did here. So if we have y squared is equal to x plus 4, then how do I solve for y? So to get rid of the square, we can take the square root on both sides. The square root and the 2 will become 1, so we get y. But remember, if you take the square root, you're getting a plus or minus as your solution of x plus 4. Okay. So if we do the same process, let's say, let's see, if we want to pick some points, let's try 0. So what happens if I plug in 0 for x here? Then I would get y is equal to the square root of 4, plus or minus. What's the square root of 4? 2. So y is going to give us a plus or minus 2. So what does that mean? Well, whenever we chose x to be 0, one answer it gave us was a positive 2, but it also gave us a negative 2. So notice that 0 is giving you two answers here. So therefore, this is not a function. Okay. All right. So click the trash can by the download button. I don't see my trash can. Oh, is that the trash can? Okay. Yes. All right. So for a shortcut, if people like shortcuts, anytime that you, oh, so let me give you, let's add a letter E here before I do letter D, just really quick. So let's say I have letter E, and the question is y equals square root of x. And I want to know if this is a function, okay? And then if you think about what we did here, we ended up with plus or minus the square root of x plus 4 for this one. Now the reason on the letter C we end up with a plus or minus is because we ourselves had to take the square root, okay? But if you look at letter E here, they're already telling us that, excuse me, that y is equal to the square root of x. So they don't want us to consider this negative here. Okay, so if I plug in 0 for x in here, I just get 0. If I plug in a 4, I'm going to get a 2. But we don't have to worry about getting a negative 2 because we don't have this negative. So the shortcut that you want to think about is if you yourself have to actually take the square root, then it's not going to be a function. Okay, so let's do the last one here. X squared plus y squared, x squared plus y squared is equal to 4. Okay, so again, this is if you forgot what the graph looks like, then your next choice is algebraically. So what I mentioned earlier is you want to solve for y first. So I'm going to subtract x squared on both sides. And to solve for y, I am personally going to have to take the square root. So once I take the square root, I have to consider the plus and the minus. Okay, so now no matter what I enter for x, I'm always going to get a positive answer and a negative answer. Okay, so my x is always going to produce a positive answer and a negative answer. So therefore, this one is not going to be a function. Okay, so again, once you learn about what these graphs will look like, then always think about what that graph might be, and that might make these problems a little bit easier to work out. Otherwise, we would have to solve these algebraically, and my recommendation would be to solve for y first, and then ask yourself if you put a negative value, do you only get one answer? If you put a 0, do you just get one answer? If you put a positive, do you just get one answer? Okay, so this was determining if something is a function, but how do we evaluate functions? So you're going to be doing this throughout the semester. Let's say you have this function and you want to know what is the function when x is equal to 2. What they're asking is what is going to be that ordered pair. So right now we know that x is equal to 2. So right now we know that x is 2. So the missing number that we want to find is y. And that's what it means to evaluate the function. So let's try the first one. So if x is equal to 2, this is my function. Anywhere you see an x, you want to replace it with the number 2. So here we're going to have 3. I see an x, so I'm going to replace it with 2. And then we're going to simplify. So 3 times 2 is 6, minus 2 is 4, and then we get our 2. Okay, what about over here? So here we have x is equal to a. So it doesn't matter if you have a number, a variable, or a picture of something, you're just going to plug it in here for x. So x is here is a, so anywhere I see an x, I'm going to replace it with a. So 3 times a is 3a. Minus 2, there's nothing else I can do here, so that would be my answer. And then the last one here, so here I have, so this should have a x. Let me just write it really quick. Oh, I got out. Hold on. Um,
Okay, guys. So let's finish this off for Miss Chuka. Says I think she lost her connection. So we're validating 6 plus h for this function. So everywhere we saw x, as Miss Chuka said, we're going to plug in the 6 plus h. So now we're going to simplify by distributing that 3. So when we distribute that 3 times 6 is 18, 3 times h is 3h, and then we have the minus 2. Then the final step is combining our only two like terms. We have a 18, which is a constant, and the negative 2. So when we add those two, we get a 16. So the answer for f of 6 plus h is the square root of 16 plus 3h, because we can no longer simplify this because of this variable h. We just leave it like that, okay? And that will be our answer. All right, so now let's look at something slightly different, okay? So don't be scared on this function. This representation here on this problem is also a function, but this one's called a piecewise function. And the reason why it's called that is, if you noticed here, instead of just evaluating one function, we put this bracket here and we can solve multiple brackets. And what this means is that on our graph, we're going to graph these two equations, but we don't want to look at the whole equation. So this item here on the side here, we're going to put restrictions on, for instance, this equation here. We only want to look at the x values that are -1. And for this second equation, we only want to look at the values that are greater than or equal to -1. And that's going to determine if we're going to evaluate our input value here, our x value. So let's go ahead and look at A. A says evaluate the function at -4. So then you ask yourself, is -4 greater than or equal to -1? No, -4 would be smaller than. So that it only applies to this first one. This first one says x has to be less than -1, and -4 is less than 1. So this -4 is only going to be applied to this first equation here. Okay, so then when we're going to evaluate A, we're going to use this first one. So is this first one, if we're looking at it as an individual, f of x is equal to -2x minus 2. So they want us to evaluate f at -4. So again, everywhere we see x, we're going to plug in that -4. Now we just simplify. A -2 times the -4 is going to give me the +8 minus 2, and 8 minus 2 is 6. So the answer for f of -4 is only going to be one answer, okay? It's this 6. Let's do B. -1. Again, is -1 smaller than -1? No, but -1 is greater than or equal to -1. So for this B, it's only going to apply to the second function or second equation. So I'm going to go ahead and use it. I'm going to evaluate f at -1 for this equation. Everywhere I see x, I'm going to plug in that -1. So we have -1 squared plus 2 times -1 minus 1. So a -1 squared is +1. 2 times a -1 is a -2. We have -1. So then we have 1 minus 2 is -1. -1 plus a -1 is a -2. So when my input value was -1, my output was -2. Okay? And the last one, C. Evaluate the function at 1. Well, is 1 less than -1? No. But is 1 greater than or equal to -1? Yes, 1 is bigger than 1. So then again, I'm going to use the same one again. I'm going to use the x squared plus 2x minus 1. Again, everywhere I see x, I'm going to go ahead and plug in 1. So we have 1 squared plus 2 times 1 minus 1. So 1 squared is just 1. 2 times 1 is 2 minus 1. So 1 plus 2 is 3. 3 minus 1 is 2. Now, one of the things that I want to point out before I move on forward is when you're evaluating functions, it's a good common practice to always put parentheses on the value that you're putting, because you want to make sure that, for instance, on the square, if we look at b here, and when we're using -1, that -1 has to be squared. So it means -1 times -1. And same goes with c. Even though that was just a positive number, is a good practice to always put parentheses of the number that you're plugging in, because that way we make sure that we are doing whatever operation is required in that function. Okay, so just keep those things in mind. All right. So now what we want to do is move to what's called the difference quotient. Okay, so the difference quotient is given in your book by this formula, and it's the foundation, and it's what we do a lot in calculus. But don't be scared. We are not going to be doing calculus, okay? We're just going to use this fundamental function or equation to just practice our algebra and practice evaluating functions, okay? So the formula here for the difference quotient is given by this: f of x plus h minus f of x all divided by h. And what this symbol means here on the side, h cannot equal 0, is you all know this is a fraction, right? This is a representation of a fraction. And when we're dealing with fractions, our denominator should never be 0. Okay, so that's what this is saying. H will never be 0 when we're evaluating our difference quotient. Now, let me show you how we're going to be using it in our classes. Okay, so your homework is going to say, use the difference quotient to evaluate this function, f of x 3x plus 1, and it's going to say, find f of x plus h minus f of x over h. So the way I like to do this is you see that this really involves 3 different parts. So let's look at it. The first part is evaluating the f of x plus h. The second part is evaluating f of x. And then the third part is plugging everything in together and then doing the division of the h. Okay, so let's go ahead and do this. So the first part I'm going to do is evaluate this f of x plus h. So again, my function that they're giving me is 3x plus 1. So just like before, in order for me to evaluate this, I'm going to substitute the x for the x plus h, and everywhere I see x in the equation, excuse me, I'm going to plug in x plus h. So let's simplify, and we simplify distributing the 3. 3 times x is 3x. 3 times h is 3h, and then this is plus 1. Now, with here, we are done because we cannot combine any more terms. We have 3 terms, and they're all different. So that's my answer. Now let's go ahead and do the second part. Okay, the second part is evaluating f of x. So basically, I don't have anything to evaluate. They're just telling me that I'm just going to use f of x just as it is. Or if you want to think about it, it's saying to plug in x where every time you see x, and we still have the same situation, 3x plus 1. So now let's put everything together. So from the first part, we had the 3x plus 3h plus 1. And then from the second part, we just had 3x plus 1. So we're going to go ahead and plug them in by doing the subtraction here. So we have 3x plus 3h plus 1 minus, and again, because I have a polynomial, meaning I have more than one term, I want to put a parenthesis on this expression because I'm going to have to distribute this negative symbol, okay? And then we're going to divide by h. So let's go ahead and simplify our numerator, okay? So we're going to do that by distributing that negative sign. So a negative times a 3x is a negative 3x. A negative times a positive 1 is that negative 1. Now we have to say to ourselves, can we simplify by combining any like terms now on the numerator? And the answer would be yes, right? If you see here, we have get my pen here. So we have sorry, I'm not be able to write. It's okay. So we have there we go. It's on the animation. So we have a 3x and a minus 3x. We have a positive 1 and we have a negative 1. So what's that going to leave us? It's going to leave us just with a 3h over h. So again, what is h divided by h? That's 1. So our final answer is going to be 3. So I just used the difference quotient to simplify the equation. Again, see, we're not doing any calculus. It's just simple algebra to practice our functions. All right, let's move on. Let's go ahead and do another example, just a little bit more complicated. Again, the best way to do these is let's do these in parts, okay? So again, just as before, let's first do our first part, evaluating f of x plus h. Again, the function that they're giving me is x squared minus 4x plus 7. Everywhere I see x, I am going to plug in this x plus h, okay? So we have x plus h squared minus 4 times x plus h plus 7. All right. Now, this x plus h squared, well, what does that mean? Well, that means I have 2 of these guys. So I have x plus h times x plus h. The negative 4 I distribute into the x plus h. So negative 4 times x is negative 4x. Negative 4 times h is a negative 4h plus 7. Now, for this this product here of x plus h times x plus h, we gotta do FOIL. Okay, so what is that FOIL? FOIL means that this first has to be multiplied with both of the terms of the other, and this term has to be multiplied with the other terms, right? So we have x times x is x squared, x times x is xh, h times x is xh, h times h is h squared. Okay, we can simplify this by combining our like terms. So we have a 2xh's, so that gives us 2xh. We have a h squared, we have a minus 4x minus 4h plus 7. All the other terms are individual, they're unique terms, so they cannot combine them. So this is what I have for x plus h. Again, let's do the second part, evaluating f of x. F of x, again, since it's saying that just to plug in x, I already have the x's, so I don't do anything. It's just using it as is, x squared minus 4x plus 7. Let's go ahead and put everything together. All right, so the third part is putting everything together. So again, the first part was this in blue, minus the second part, which is just the function itself, x squared minus 4x plus 7, divided by h. Let's go ahead and first start by distributing that negative, or the subtraction. So we have a negative times x squared is a negative x squared. Negative times a minus 4x is a positive 4x. And then negative times a positive 7 is a negative 7. Now we want to see if we can combine terms. And we can. An x squared with a minus x squared, that becomes 0. A minus 4x with a positive 4x, that also becomes 0. A positive 7 with a negative 7, that becomes 0. So we are left with only minus 2xh plus h squared minus 4h. So now it's just down to this division. Now let me see how we have it here. So yes, for me, this is the ideal way to do this. Since the numerator has 3 terms and all 3 terms share a like term, which is the h, I'm going to factor that h out. So when I do this, now it's easy to see that when I divide h by h gives me 1, my final answer is just minus 2x plus h minus 4. Okay. Now just also one tip, when you're plugging these in into your homework, the order doesn't matter. Okay. We like to have them like this, but you can put this in any order as long as the sign is correct. Okay. All right, so this is our answer. Let's go ahead and review domain. Okay, now, as Ms. Chuka said, domain refers to all the x values of the function, or again, as some instructors say, all the input values. Okay, so, and we're looking at this graph, and we want to look at all of the values that this graph has. One of the things you need to pay attention is that in this graph, we have a line here. We have an arrow on this right side, and we have an arrow on the left side. So what this means is that this graph, even though we're only seeing a snapshot of it, 10 values all around, right? 10 units to the from 0 to the right, 10 units to the left of 0, 10 units up, 10 units down. This line goes forever to the right and forever to the left. Okay, so for instance, this problem, and we wanted to find the domain, this graph is going forever to the left and forever to the right. So one of the things we need to practice is first, if there are equations or graphs have restrictions on the domain, that means that are there certain values that we cannot use that will not give us an answer when we plug in a value for x. Now, one of those, we have several equations that will give us restrictions on our domain, and we'll cover some of these. So the first one that we like to talk about is the fraction equations, right? So when we're dealing with a fraction or a fraction function or a rational function, we never want the denominator to ever be 0, because if the denominator is 0, we're going to get an error. So hence, we will have a restriction on our domain. We cannot use the value 0 for x, okay, when we're dealing with fractions. The other one, when we're dealing with the square root or a square root function, okay? Square roots, we are not allowed to use negative numbers. We cannot evaluate the square root of a negative value. Now, this is just for right now. Later on, well, there's a loophole, but for this time being, we cannot use negative numbers for square roots. So again, when dealing with square roots, we will also have a restriction on our domain. Okay, there's we won't be able to use negative x values when dealing with the radicand. Okay. And then the last one is if we are when we're dealing with logarithms. So if yes, then there will also be restrictions. But now we'll deal with logarithms. There's a section for it, and we'll go over some of those features that we can use. So if you answer to all these three questions no, then your domain will be from negative infinity to positive infinity. So this is an interval notation. That means that this has no restrictions. It's like saying that the graph is going forever to the left and it's going forever to the right. I can use any x values um, to evaluate my functions or graphs. Okay. All right. So let's look at these. Find the domain of each of the equations below. So the first one, okay, hopefully with our presentation, you'll be able to answer these super quickly and very easy because now you're getting familiar of what we're looking at here. So here, if we look at A, I know that A, we've already covered it, is in slope-intercept form. It's an equation of a line. And if we're dealing with a line, the line is going forever to the left and forever going to the right. So then I know that this graph is not going to have any restrictions. But again, if we go through the features that we were talking about, saying, do you see a fraction here? No. Do you see a square root symbol? No. Do you see a logs? No. So none of that. So then this equation, its domain for A um, is all real numbers, right? So so an interval notation is from negative infinity to positive infinity. This is going to be my domain, right? So let's go ahead and again, if we were to graph it, as I mentioned to you, I know that this was going to represent a graph, and you see my graph is a line that has arrows both to the left and to the right. So that's also what tells me that the domain is negative infinity to positive infinity. Okay. So let's look at B. Okay, B is a different shape. Okay, um, but on this one too. Okay, you say to yourself, does this function have any fractions? No. Does this function have any square roots? No. Does you see the word log on here? No. So since I don't see any of that, my domain again is from negative infinity to positive infinity. Okay, and again, if I were to do the graph, this is called a parabola. It's like U-shaped graph. But if you see again, this graph has an arrow on the left and an arrow on the right, which is telling me that this graph is going forever to the left, forever to the right. So the domain is from negative infinity to positive infinity. Let's look at these others. Okay, so we have y here. Excuse me, a. We have y is equal to 1 over x plus 4. Oh, we got to check. We are answering yes to one of our problems that could have a restriction. We see a fraction here. So what is the value that we never want to see for a denominator value in a fraction? Which is 0. So then I cannot use 0 as an input value for this equation. So the answer for the domain for A on this one, since I cannot use 0, we need to exclude it. The way we're going to write it is in English is the domain is all real numbers except 0, and the way we write it is in two parts. Okay, so keep in mind we read graphs from left to right, and that's how we're going to also write our interval notations. Our furthest left is the negative infinity. Now I forgot to mention, but if you saw when I was writing the negative infinity to positive infinity, we use parentheses for the for the infinity symbols. Please never use a bracket, because a bracket means that you want to use that value. And infinity, there is not a number. An infinity symbol is a number that is continuously going. It never stops. So always use parentheses to include when using the infinity symbol. Okay, so we're from the left, negative infinity to 0. But again, I have to use a parenthesis here because I cannot use 0. So this interpretation on the left here, the negative infinity to 0, is talking about all of them that I can use all of the values that are negative to the left of 0. Okay, but we also can use all of the positive values. We cannot use 0, but we can use all the positive values without getting an error, right? So we put this symbol here. This symbol means and. Um, in interval notation. So all the negative numbers and all the positive numbers. And again, in interval notation is starting at 0, but we're not using 0, so we use a parentheses all the way up to positive infinity. So this is my domain for this equation right here. So let's look at very similar part B. And we're looking at part B. If you don't see it, well, first we see that we're dealing with a fraction. So we have to say, uh-oh, there might be a restriction on this problem. So then we see here, the denominator on this fraction is a x minus 6. And again, if you don't see what the value that will give you 0 on here, do it algebraically. Solve for, set it equal to 0 and solve for x. And if you see here, if we plug in 6 down here, 6 minus 6, it's going to give me 0. So I can use all real numbers except for 6 now. So it's going to be the same as A, but now my domain for this problem in interval notation, again, is from negative infinity to 6, not using 6, and, or union, from 6 to positive infinity. Okay, so again, when dealing with a domain for your homework, you have to answer them in interval notation. And you have to be careful whenever you have an equation that has a fraction, a square root, or the word log on there. Okay? All right. So let's look at, if we were to graph these, you can see that why the domains are what they are. So if we were to graph these, if you see here on the first one for A, of left of 0, we have an arrow that's going forever to the left. And the arrow here is going forever down, but it's never crossing or touching 0. This vertical line here has a special name that we will cover later, okay? But then to the right of 0, which are all the positive values, this has an arrow going up, but it's never going to cross or touch 0, and it's going forever to the right. So that's the interpretation on this one. Similar with B. If you see here, at the value 6, and this one should have been the other way. This is saying it's negative 6, and it should be 6. It should be on the other side. But this should have been 6 here. So here to the left of 6, you would see that the graph gets closer and closer to it and doesn't touch. And then the other one would have been the other side at 6, and it's going forever to the right. So again, keep this in mind. This shouldn't be negative 6. It should be 6 on the other side. Yeah. All right. So let's find the domain of the equations below. Now we're answering yes to, we have a square root example on here. So what do we not want when dealing with square roots? We cannot put negative values in here. So what I tell my students is, look, to solve for this, to find the domain first, do 0. Okay, I can take the square root of 0. Now, on this first one, it's very easy to see that I cannot use any of the values that are left from 0, because all the values from left of 0 are going to be the negative numbers, and it's just the direct input of a negative value. So the domain for this problem, okay, is going to be all of the values that are to the right of 0. So here, when I'm writing this one, if I write it as an interval, x has to be greater than or equal to 0. That's where my domain begins. That's when I have a solution and I don't get an error on my calculator. So when I write this as an interval notation, the domain is, now do you see that because I can use 0, I put a bracket in here. Bracket means that I can start at that value. It's okay to start at that value. And again, we're reading from left to right. My starting point is 0, and I can use all the values to the right of 0 all the way up to infinity. And again, please never use a bracket symbol for the infinity symbol, okay? Because an infinity is not a number. It just keeps on going, never stops. All right, so let's look at the second one. Now on this one, the same situation here. What I tell my students is, Um, First, let's find out, let's start at 0. So is there what x value that I can put here that will give me 0 for this square root? And if you don't see it, you can see I'll solve it algebraically. But if you put -5 for x, -5 plus 5 is 0. Okay, now can I use values to the left of -5 or to the right of -5? So here, it's easy to see when it's in an interval notation here, because here the value of x has to be greater than or equal to -5. Why? Because check it out. If I had -5 and I use a value to the right of -5, so a value to the right of -5 is -4. -4 plus 5, that's a +1, um, which I can use. And if I continue going to the right of -5, -2, -1, 1, 0. From then on, they're all positives. But what happens when I go to the left of 0? To the left of -5. If I put in to the left of -5 is -6. -6 plus 5 is going to give me a -1. And it's going to be that for all of the values that are going to be to the left of -5. So all of those values I cannot use. So my starting point is at -5, and I can use all the values to the right of -5. That will give me positive values. So again, the interval notation for this one is bracket -5, because I can use -5. It's going to give me 0. But then after that, it's all the values to the right of that. So it's comma to positive infinity. Okay? So this is how we write the domain for our equations and functions. All right, so if you were to see the graphs, you would see how this makes sense. For this first one, the graph here starts at 0, and there's a filled circle here, and it goes forever to the right. So that's what my domain is, from 0 to positive infinity. And if I look at this one now, too, I start at -5, including -5, and then it goes forever to the right. Because of my arrow, it's going to positive infinity. And again, we love graphs because we can see the domain visually, right? Okay, so now let's go into evaluating functions graphically. Okay, so now if we have a graph here, and we have this weird looking graph. Again, let's first analyze this graph a little bit here. Okay, um, at this point here, you see my y value is 5, and to the left of my 5, I have an open circle. When we have an open circle, that means that that value, thank you, does not exist at y equals -5. That's so, but it exists. All of the values below it, they do exist. But then we have a filled circle at this right side of the graph. This value does exist. Okay, so open circles means that that value doesn't exist. A filled circle means that it does exist. So now let's look at this. It says I want to evaluate a at f at -1. Okay, now what we're talking about is when we're evaluating these functions, we want to evaluate our input, and that's what we said. As Ms. Tuca had mentioned when we started, our x has to deal with a domain, all the x values that that our graph or functions represent. The output or the y values is the range. It's all the y values that our graph or function represent. So when we are going to evaluate our graph, first let's look at the domain of what they're giving us here. So if I would go here, my x value, if I am reading graphs again from left to right, my first x value here is at -2. Okay, but at -2, when I go up, you see that we have that open circle. That means that at -2, I start there, but that value doesn't, I can't use it. So that's why we have that parentheses at -2, that I'm starting at -2, but that value does not exist. And then it's going all the way up to +2. And here we do have a fill circle. So at 2, it does exist. So then that's why I'm going to be using the bracket. Okay, now let's look at the range again too. The range here, we see here, it starts when we read it from the bottom up. Okay, think of you're laying down and you're still doing from left to right, but we do bottom up. But see, this graph starts at here, believe at -4, and since it's just the line is touching, we can say that the dots are there, that they're filled in, right? So it does start here. Now, this is when it's going to be tricky. It goes all the way up to +5. All the y values go up to +5. But we have to include 5 because even though it doesn't exist here on the left, it does exist on the right. So the range, when I write it in interval notation, it's going to be both brackets. Bracket -4 and +5. Okay. Again, even though it doesn't exist on the left, it does exist on the right. So now let's go ahead and answer our questions. Here, they want me to evaluate what is the y value when x is equal to -1. So all you have to do is go to the graph, go to where -1 is, and then see where the graph is on the y-axis. So we would go down, and then we would see that at -1, we have looks like -4. So the answer would be for A, -4. Let's look at the value x value at 0, or evaluating the function at 0. When I input 0, what is the y value? What is the y value that's going to give me? So I follow it down to where the graph is, and that looks like it's -3. So my answer here would be -3. And I do the similar same. I put evaluate the function at 1. I want to follow it. Where is it on the graph? The answer would be -4 again. And then the last one, evaluate the function at 2. So the function at 2, the answer would be 5. And because it's a filled circle, the value is there. So that would be my answer. My answer would be 5. So these were the x values, the input, and the output values, my range, or my y values would be these here. Okay. All right. All right, so let's look at this one. Let's evaluate this one. Again, use the graph of the function, find the domain and range. Use the graph to find the indicated values. Okay, so let's first find the domain and range of this function. So here, again, the domain refers to all the x values. So if we were reading this graph from left to right, well, since there's an arrow here that's going forever to the left, so we know that's going to start at -infinity. And then we're going. Now here we have a fill circle, so it's still um, we still have an x value here, even though that there's an open circle here. But if we continue going on, this line picks up where we left off, and again we have an arrow to the right. So then the domain for this graph is from -infinity to +infinity, even though there was a break. Okay, I have x values for all. Now, if we look at the range, again, we're looking at the range from bottom up. So where do we start? We start at -2, but oh, we have an open circle. So that means that we're going to start there, but we cannot include that number. And we do that by putting, again, the parentheses to the -2. And then if we see here, the graph, we have arrows pointing up. So that means that it's going forever up. And the symbol for forever is infinity, right? So our range is going to be from -2 to infinity. Okay. So now we can go ahead and answer our problems. The first one, evaluate. So now we can go ahead and answer our problems. The first one, evaluate f of 2. So everywhere we see the where it crosses our graph, that's our answer. And that looks like it's 0. Okay, so let me just go through them really quickly because I am out of time. I got a minute, so I'll just write down the questions or just show you the answers, okay? Now, keep in mind, I'm going to stop here, but if you haven't done so already, you could have downloaded our presentation just by clicking that arrow with the box in. If you weren't able to make it, or tell your friends that these sessions are recorded and you can find them later on. Ms. Chuka, any last words you want to mention to our students?
No, just thank you for joining us. Hopefully, we'll see you all next week.
All right, thank you very much, Ms. Chuka and Mr. Carrizales, for this wonderful presentation. I would like to remind everybody that you can download today's presentation by clicking on the down arrow that you see up on your right upper hand corner. And also, if you want to join us for next week, February the 2nd, Happy Math Hour will be on factoring. So come and review the different factoring methods at 11 a.m. And then also the academic success presentation for distance learning with Luz Cadena. That will be Friday from 1 p.m. to 1:50 p.m. Okay, so thank you very much for all the students who joined us today. And if you have any questions, please let us know. Also, I would like to invite you to visit our YouTube channel if you want to review this presentation. It would be uploaded into the YouTube channel also, and the link is on the chat. So if you have any questions,